So, okay, I'm going to give some motivation about this problem. I hope that doesn't take too much time, but let's do this. So, everything started, or some people were studying this, the stability of this theorem. So, this theorem was proven by Shen and Yao, and then by Witten. And it says the following. So if one has a Riemannian manifold, and I'm going to state it for dimension 3, which is complete and asymptotically flat, then the scalar curvature of this manifold is non-negative, then the ADM mass of this manifold has to be greater or equal than 0, and equality holds if and only if our manifold is actually the Euclidean space. So let me write it this way. Okay. So what does asymptotically flat means? It means that outside a region, M3 looks like Euclidean space, and that the metric also looks like the one in Euclidean space. So let me just draw a picture. I'm not giving this definition exactly, but what you have to think, or this is actually the trivial example, and it looks like this. So there is some region in which we don't know what is going on, so it's this part. And here I might have boundary, or I might not have boundary. And this is going to approaching flat space. Okay, so ADM mass is an integral over, because you know that your manifold is getting closer and closer to Euclidean space, so actually you have a charge at infinity, and you have to integrate over the spheres in these manifolds some quantity that depends on the derivatives of the metric. Okay? If you need a formula, I'm going to write a formula for the special case of manifolds that I'm going to use, just if you need a formula. Okay? So then this is a theorem, and we have a rigidity statement. So the question is, what about if we take a sequence of Riemannian manifolds that satisfy these conditions, and I decide that the ADM mass of this sequence of manifolds is converging to 0. So what do I get in the limit? Do I get Euclidean space, yes or no? And if you know about metric spaces, you can think of Gromov-Hausdorff convergence, but there are many counterexamples with Gromov-Hausdorff convergence. You can add more conditions, so you can define a class of manifolds and say, okay, in this class of manifolds, I'm going to prove that the sequences converge to Euclidean space with respect to Gromov-Hausdorff distance. But I'm not going to do this. I'm going to use another type of distance. So question or answer. Well, question, take MJ, GJ as in the previous theorem. Is there, or the, does MJ, GJ converge to Euclidean space? And here let me allow n dimensions with respect to some topology. Okay. And so I'm telling you that there is a class. So actually, this was done by Huang Lee and Sormani. And they define a class. So answer, the answer that they gave is yes for a class of manifolds that I'm going to denote by G because they are going to be graphical manifolds of dimension n, and they depend on some parameters. So let me write the parameters are 0, d, gamma, and alpha. And using intrinsic flat convergence. Okay, so how do these manifolds look like? So, yes. Yes. Okay. Non-negative, yeah. Okay, so how do these manifolds look like? These manifolds are actually graphs. So M is in this class, and I'm not going to write now the parameters, if there exists an isometric embedding to Euclidean space of dimension one more than the manifold. So this is a Riemannian isometric embedding. And isometric embedding, and actually the manifold contained here in Euclidean space is actually the graph of a function f. So this f should be defined in Rn minus a region. This is an open set to R. So this is a part where we don't know what is going on with our manifold. So we might have boundary, this U might be empty, and then we don't have boundary. Okay, so this, and I'm not saying, I don't know, this is not good. And let me explain what these R0, D, and gamma means. This alpha, actually, we only need it for dimension 3 and 4, so I'm not going to talk about this, but let's see what this R0, D, and gamma means in this picture. So let's assume that this is the R0 level set. So in my parameters, I had an R0. So this is the R0 level set. And actually, I'm going to write it this way. Well, I don't know if I'm going to need this notation. Okay, so here I have this set. And what I want to know is that this part below this level set doesn't increase that much. So the length, the distance between any point here in this surface to all the points here, it's less or equal than D, the length distance. And then I had a gamma parameter. So the gamma parameter means that if I go to the level set sigma R0 over 2, so it's here, then the gradient of f is less or equal than some gamma. So I have a Lipschitz condition outside. Remember, these manifolds are asymptotically flat, so actually this is like an asymptotically flat condition, uniform, okay? And then the other thing that I know is that this U, so this part in which my function is not defined, should be contained in a ball of some radius, uniform radius, okay? So that's my class of manifolds, and they said that, okay, you get, whenever you have a sequence of manifolds in this class, and if the ADM mass is going to 0, then you get convergence, not to this, so I'm going to explain what they do, okay? But basically, they wanted to prove this. So first, because we are going to use intrinsic flat distance, this is about flat distance, And this flat distance is defined for currents in metric spaces defined by Ambrosio and Kirchheim. And the currents defined by Ambrosio and Kirchheim have finite mass or finite volume. So this doesn't have finite volume, so I need to do something. And well, Huang Lee and Sormani, what they did is the following. So define omega r equal to this region. Okay, so now this is compact. And what they want to do is study if for a sequence, so I'm going to write this, if this converges in intrinsic flat sense to a ball, to Euclidean balls of radius r, okay? So that's the question. Do we have this? And I'm going to say a little bit about this convergence, but that's the question. So what they did is the following. So they have a proposition, and they show that for manifolds in this class, I'm not going to write the parameters we have. Actually, let me write a sequence, and let's write that the ADM mass is going to 0. Okay, so we have one control in the volume of this sequence. So actually, the volume of the MJs is converging to the volume. Oh, sorry, this should be omega r's. So this is true for any r greater or equal than this r0. So the volume of these omega regions converges to the volume of the ball of radius r. Number 2, the volume of the boundaries of the omega regions, J. I'm going to write this. Is bounded by some constant that only depends on the parameters, and the diameter of the whole region, omega j, is bounded by some constant that only depends on these parameters. This is for all j, for all j. Okay, so questions? So this is using like actually I skip one condition for the functions, but it's basically using the conditions of the functions and using Penrose inequality, because you know that if the mass is going to 0, then the boundaries, I mean in these regions, I have two boundaries. So I have this boundary, or might have this boundary, and then the outer boundary. So using Penrose inequality, these boundaries, the masses of these boundaries or volumes are going to converge to 0. Okay, and now I just need to worry about these exterior boundaries, but here I have this gradient inequality. Okay, so once that we have this, if you know about integral currents, this tells you, or this is a theorem by Stefan Wenger, that says if you have actually a volume bound, an area bound, and a diameter bound, then this sequence, or there is a subsequence that converges to an integral current space. Okay. So by Wenger, let me write omega j. I'm not going to write the subsequence, and now I'm going to introduce notation of integral currents. For some subsequence, and I'm going to write an F. Okay, So what does this mean, or what does an integral current is? Well, this is a metric space. This is a current, and I'm going to say what is a current. But so here I actually have, let's say these are dimension n. This is going to be an integral current of dimension n. And then here there is some subtlety that this integral current is defined in the closure of X bar, in the completion. And then another thing is that the set, this is a smaller set than the support of the current, and I'm going to say something about this. The set of this current is actually X. Okay, so then what is a current? A current is going to be a functional that takes first, and here I'm going to write T in, no. So it's going to be a current of dimension n in the space, metric space set, and set should be complete. In this case, so for Ambrosio-Kirchheim, this set should be complete, and you can generalize this definition of currents in metric spaces for non-complete spaces, and that was done by Lahn and Wenger. Okay, so then you take here n Lipschitz functions, and you get a number. So this has to be multilinear and has to satisfy some continuity condition. Basically, the continuity that you ask is the continuity in this part. Pointwise continuity of Lipschitz functions should converge to T evaluated in the limit of that thing. And then something to say that the current is 0. So let me just write it. This is equal to 0 if there exists a pi I. So this is a function that is made out of n Lipschitz functions. So if some pi I equals a constant in a neighborhood of the support of F. Okay. And number 4, I told you this definition says that the mass has to be finite. So there exists a mu Borel measure on C, finite, and such that you can bound this operator in this way. So less or equal than the integral of F with respect to this mu, and here I have to write the product of the Lipschitz functions pi, which I'm going to write this way. Okay, and so there is the minimum mu that satisfies this condition, and this is called the mass measure. So P, mass measure, and is the minimum mu that satisfies that condition. And then I'm going to need this notation, mass of T equals just the whole measure of the space with respect to this measure. Okay, and then one can define one push forward. I'm not going to define it, but what you need to define push forward is a function phi from one metric space to another metric space, which is Lipschitz. So everything behaves nice because your domain has Lipschitz functions. And also, one can define a boundary operator. And this is just a boundary operator. I mean, it doesn't take one current to another current. So if I have a current, and I take its boundary, so f of pi, what it's going to do is take t, 1, f, and pi. So this is an operator that takes functions in this product, and here should be n minus 1. Okay? Good. I don't know, are there any more questions? Otherwise, let me skip details about integral currents. And Okay, no, just to clarify. For integral currents, which are the ones that we have here, so what we can do is write this T as a sum of currents. So let me just write it. T can be decomposed as push forward of some currents. These theta's i's are functions in L1 Rn. And because I want them to be integral, here I can write that. Okay. And another condition of this is that, so boundary of T has to be a current. So that means integral, that I can write it this way, that the boundary of T is also a current. And sorry for all of this. What? Yes. Yes, thanks. And okay, I have a space here. Okay, so the thing is that we have these regions and we want to prove that this x dt is actually an Euclidean ball with the Euclidean distance and with the canonical integral current that comes from the ball. Okay, so that's actually what we want to do. We want to prove that x dt equals ball of dimension n, the Euclidean, or let me write it E, and this current that maybe I didn't define, sorry. Okay. That's what we want to do. And what Huang Lee and Sormani did was the following. So proposition HLS, sorry, I don't write everything. And it says the following. Under the conditions that I already have, there exists a psi from this limit space X to Rn, actually Rn plus 1, which is 1 Lipschitz. And basically, this is an Arzelà-Scully limit of the Riemannian isometric embeddings that I have for the MJs. Okay? And what else do we know about this map? We know that, and let me, yeah, oops, sorry. Okay. We know that the support of this map is contained where I want, so the ball cross 0 and the following conditions. So I have one about the boundary. So if I push forward the boundary of this current, this is going to be the boundary of B cross 0. Okay, number 2, if I take the lim inf of the masses of these currents, so actually this is going to be, let me write it this way, the volume of the omega j's are, or let me write it like lim, this is the volume of the ball of radius r. And number 3, a psi or psi is by Lipschitz from the support of boundary T to boundary of B. Okay, so what do we get, or how do we get this? Well, I told you this is an Arzelà-Scully limit, so it's going to be 1 Lipschitz. The volume bounds follow from what I have here, and this thing just follows because we have this gradient inequality for the functions f. So we will have this by Lipschitz condition there. Okay, and here notice that the boundaries, even though our sequence of manifolds might have two boundary components, at the end we just get one because the inner ones disappear because of Penrose inequality. Okay, so we have this, and they claimed that then C has to be an isometry, but they didn't prove it. So then with my collaborator, we proved that this is an isometry. So let me state the theorem. EHM, yes. Yes. Yes, yes. Or maybe.
Just to keep track, I mean, nothing. The support of side.
Yes. Okay. Okay. So theorem. The mean with P, and it says, well, it basically says what we have in this other part of the blackboard, but let me write it anyway. So it says, let X, D, T, an n-dimensional integral current space, and C, from X to B, and I can write it actually in this way, or let me write it to Rn, such that, and then I'll just basically copy the conditions. C push forward partial T equals to partial B. So this B is the unitary ball. I'm just rescaling everything, and then to the mass of T equals the mass of the unitary ball. So this means our Lipschitz map is preserving the volume. And number 3, C is injective. So I don't need the by Lipschitz condition from support of boundary T to or boundary of V. Okay, so that's then C is an isometry. Okay. Let me remark about this theorem. So before we posted this result, Basso, Kreutz, and Sultanis proved a similar theorem. And this was because actually Christina announced this problem. She said, okay, can you prove that this is an isometry in a conference? Yes. Yes, I forgot to write it.
Yeah.
Okay. Yeah. Yes.
It's okay.
No, but it's okay. It's okay. And so people knew about this problem, and these people got a result before us. But they didn't know where this problem came from. So my motivation is this positive mass theorem or rigidity of positive mass theorem. So they didn't know about this bijective condition on the boundary. So what they wrote is the following. Instead of 1, they wrote C push forward T equals to B. That's 1 prime for them. And then 3, they wrote basically this condition, but for the boundaries. So mass of partial T equal to the volume of the sphere. Actually, they did a little bit more. So let me change this, and this is a convex set. And well, this is the boundary of the convex set. And they proved the same thing, that C is an isometry. Okay? And in the second line, here, one, number 3. I'm sorry. Okay. Thank you. Okay. So they proved this, and our proof is very, very similar. And then they added more results to their paper, which now makes our papers very different. But then another person came, and this is Roger Sust, and actually he changed this completely. And here, let me write, this is a manifold. So this is a Lipschitz manifold. Well, n-dimensional can have boundary or no boundary. So actually, if there is no boundary, we don't need this number 3. Then this is an essential length space. And this basically means that between 2 points, I have a lot of curves that join these 2 points. And the other thing is that they ask infinitesimally Euclidean. And what does it mean? Well, that the tangent spaces of this manifold are Euclidean, almost everywhere. Okay, so if you have these conditions, and here you have to, well, I'm going to change all of this. Here you have this, and here you have volume of M, where volume of M, it's Hausdorff measure of dimension N, okay? And basically, this condition without the injective part. So it means support of boundary of T has to go to boundary of M, okay? So if you have these conditions, then you also get an isometry. Well, yeah. So questions, and how much time do I have? Almost 0. Oh, okay, thanks. Thanks. So now I need to learn how to erase. 10 minutes for this. So I want to say that Sust, so the last work about this being an isometry, he gave some counter examples, or some examples saying that essential length distance cannot be interchanged by a length or a geodesic space. And also that you cannot replace, oh no, well, that's another example that is given in Basocroid-Sultanis, but it says you cannot replace this infinitesimal Euclidean condition. And let me. And now what I want to do is, or show you, it's a very silly example about why we need conditions on the boundary. And probably you can come up with better examples, but I like this example a lot. So I'm in R2, and my metric space X is going to be the following. So I'm really bad drawing. So these are balls of the same radius, and let me choose as X this part and this part. So this is going to be X. And then my map, what it's going to do is put these 2 halves make them a circle. So this is x with the Euclidean distance, and well, this is a disk. And so here the map that translates this part to this and this part to this is going to be an isometry. It's going to preserve the area, but notice that here the boundary, this part, doesn't go to the boundary of this disk. Or also check that the mass of the boundary here, in case of Basocroy-Sultanis, is bigger than the mass of the boundary here, okay? Because we have this segment. So conditions on the boundary are needed. Well, but this is disconnected, so maybe you can, oh, and the other example, this is the one by Sust, is the following. So here I have, so I want it to be decreasing, so I guess here is S2 round sphere. And here what I'm going to do is to an equator, this equator, the distance that I'm going to put here is going to be 1/2 than the original distance. So going from here to here, I have to take curves that go from here to here, from here to here, and from here to here. Let's say infimum of curves that do this, and here is 1/2 the original distance, and here the original distance, and here the original distance. Okay, so this equator looks smaller. And so I have, again, one Lipschitz map that preserves the volume, but doesn't satisfy that it's an isometry. And you can make this example with boundary if you got some part. Yes. Yes, and this is example that this is, again, a length space, and still you don't have an isometry. Okay, so how do we prove that theorem? So let me give you an idea. Okay, and maybe I need colors. So what we have is our metric space X here. Here I have my map C, and here I have a nice Euclidean ball. So what we are going to choose, and then let me check my picture because I'm really bad at drawing and I don't want to mess up with this. Okay, so, and let me draw it this way. So we choose a vector B, which is going to be in the sphere -1, so unitary vector. And then we have B perp. So we choose a point Z here, and we are going to foliate our ball with this direction. So actually, I'm going to use the projection to be perp, and then get this type of foliation. So these are one-dimensional segments. So one-dimensional. Well, I don't know if segment implies that it's one-dimensional. Okay, so those are lines. Okay, so what we have here is the current C push forward T, which actually we know it's a current B. And what I'm actually doing is slicing with the projection to be perp, and then at the value set. So these are one-dimensional currents. So they look like this. So actually this is equal to some line that passes through set. Okay, and this is my alarm because I should hurry up. Can I? Sorry. Okay, and what do we do in this part? Well, we are also going to slice T. So I slice T with a map psi composed with P, and let me write here set. So now this is a one-dimensional current, integral in X, and this is a one-dimensional current in Rn. Okay? And what I want to say is that I can pass my problem to one that is one-dimensional. So I want to conclude that this current that I have, and let me write it as Tz, this is just equal to a current that comes from a geodesic in our metric space. Okay, so I want to say this is a geodesic, and then I want to put all the information together once that I know that the problem works for one-dimensional integral currents. Okay, and because of the volume, because we are preserving the volume, we can actually prove that this map, psi, is injective almost everywhere, where the measure that I'm using is the T measure, and also that the multiplicity of this is going to be 1 almost everywhere, okay? So then you put all together and you conclude that psi is an isometry. So basically, I'm sorry, just to say this again. You first say that psi is an isometry in these one-dimensional slices. You can do this for each V, so in particular for a dense set of V's. So then you get geodesics, or that your map C is an isometry in all these geodesics in almost all directions, and then you prove that it's in the whole space.